Okay, guys, we're gonna try and wrap up chapter 3 with this lecture. So we're gonna cover the rest of cyclohexanes and conformations, and then we're gonna look a little bit at physical properties of alkanes before we move on to chapter 4. Okay, so let me share my screen. One thing I want you to appreciate is that there's something called cis-trans isomerism that you're going to see in double bonds, which are alkenes, but also in cyclic structures, are cycloalkanes. So cis-trans, these are isomers. So they have the same molecular formula. They also have the same connectivity of their atoms, but they have an arrangement in space that cannot be interconverted by rotation about sigma bonds. So let's look at that. Here, I'm looking sort of at a flat 5-membered ring structure. So here's my flat structure. My dog's going crazy in the background. Notice that this CH3 and this one, they're on the same side of this ring. So this would be cis. If the two substituents are on the same side of the ring in 3-dimensional space, they're going to be called cis. Notice here, I have this methyl group and then this methyl group. Those are on opposite sides. One is on the top face of that ring, and one is on the bottom face of that ring. So one is on the top, one is on the bottom. That would be considered trans. Now you're going to see this sort of thing a lot. If this bond, if they're both hashed, or if they're both folded, that's going to be cis. That means they're on the same side. If one is hashed and one is bolded, that means it's going to be trans. So notice I could also do this, and because they're both bolded, this would also be cis. Or I could also have it drawn where this one is bolded and this one is hashed. But one is bolded, one is hashed. They're on opposite sides of the ring, so that's going to be trans. Again, if you have to, build a model. I strongly encourage you to use your models when you're working through problems and homework, and even when you're taking exams. If you have your models next to you and you're able to build things, if you get confused, it's going to make a lot more sense to try and figure things out. So a cyclohexane ring is commonly viewed sort of as this planar hexagon, and I look at it from one side or the other, just like before. If you guys have taken biology and you're looking at sugar chemistry, a lot of times you're going to see sugars sort of represented like this. So this is trans because one is on the top and then one is on the bottom. They're on opposite sides of that ring. Notice I have one bolded and one hashed, and that's going to represent that trans. Now notice that these are both down. So if I call them these both hashed, where that means they're both facing on the same side of that ring. When they're on the same side of the ring, they're called cis. So you need to pay attention to how these compounds are represented. A lot of times in organic, we're going to use the bolded and we're going to use the hashed wedges in order to convey this 3-dimensional information. So you really have to pay attention to what these things look like with these bolded and hashed wedges. We can also represent a cyclohexane as my chair conformation. Here, determining whether something is cis or trans is a little bit more difficult because I have those ring flips and because my equatorial positions sometimes are a little harder to read. The basic idea is if something is up, it's going to be cis. If something is down, it's going to be cis. If I have up, down, that's going to be trans. That up and down is where is the bond pointing? Does the bond that is bearing the substituent pointing up or pointing down? In this, this is trans 1,4-dimethyl cyclohexane. It's trans because I have an axial up and an axial down. So that's down, up, right? So that means it's trans. This methyl group is pointing on the top on the top face. This is pointing on the bottom. Both of these are axial. So this has diaxial methyls. If I do the ring flip, I am not making this a different, I'm not going from the trans to the cis or anything like that. I'm not breaking bonds. I'm not rearranging atoms. I'm just moving them by bond movement. But notice what was axial becomes equatorial. So these axial bonds become equatorial in the ring flip. So again, this comes down, this bond goes up. This is equatorial up, which is this same methyl group. This is equatorial down, which is this same methyl group. So now this is di-equatorial. Those methyl groups are each in an equatorial position, which means this conformation is much more stable. So you have to be able to recognize cis and trans using chair conformations. Are the bonds that bear the substituents in relation to each other up, or down, down? That would be a cis conformation, or the cis structures, the cis isomer. And then if they were up, down, or down, up, that means I have the trans isomer. Remember, every chair has 2 ring conformations. It's a ring flip between one conformation and the other. Anything that was in an axial position becomes equatorial in the ring flip, and anything that was in an equatorial position becomes axial in a ring flip. So here I go diaxial, diaxial. It flips to di-equatorial, di-equatorial. This is much more stable because my larger groups have a lot more room in those equatorial positions. So I could ask you, draw the 2 chair conformations for trans 1,4-dimethyl cyclohexane. You would need to draw these 2 structures, and then I could ask you, determine which of the 2 ring structures, which of the 2 chair conformations are more stable, and explain your answer. In that case, you need to be able to determine that this is more stable because the larger group is going to be in the equatorial position. Remember, on both sides, this is going to have these diaxial interactions, all right? Here, going down, I have those diaxial interactions on this side and on this side. So that makes it less stable. A lot of times when I have multiple substituents, I'm going to use those solid or dashed wedges in order to show the positioning. By default, sort of by convention, when I use a bolded wedge, that's considered to be up. And then when I use the hashed wedge, That's considered to be down. So this is trans because my chlorine is up and my methyl is down. To draw the two ring conformations, I'm going to start where my chlorine is up and my methyl, this is 1, 2, is down. This clearly is a trans relationship. This is axial, this is axial. When I do the ring flip, now I have something that is going to be equatorial and equatorial. Well, the methyl group is certainly larger than a hydrogen, and the chlorine, because it's in the second row, is going to be a little larger than the hydrogen. But what you want to say, if I had to say, well, which of these is going to be more stable, it would be this, because the non-hydrogen groups, the methyl and the chloro, which are larger than hydrogen, are going to be in the equatorial positions. So one of the questions I might ask you is draw both chair conformations for the following molecule. When you want to think about this, this is carbon 1, 2, 3, 4, 5, 6. So I have a substituent on the 1 and the 3 carbon of the cyclohexane. Notice this is bolded up, this is hashed down, so this would be trans. So I want to make sure that whatever structure I draw is going to be trans. This is bolded, so this is going to go up. And this is hashed, so this is going to go down. So the first chair, I'm just going to draw a chair, and then I'm going to label 1, 2, 3. And I have to line up this 1, 2, 3 up here so I know what I have. I'm going to put my ethyl up, which is on this carbon on axial position. And then I go up, down, up, down, right? So my axial goes up, down, up. My equatorial goes down, up, down. This would just be hydrogens here. So what I have is my ethyl is axial and my methyl is equatorial, right? And this is one of the chair flips. When I draw the second chair, I have to make sure that the ethyl group is going to be equatorial. Remember, this comes down, this goes up. I still need a 1, 2, 3 relationship. My ethyl still needs to go up, so it's going to be equatorial up. My methyl still needs to go down, so it's going to be axial down. So which one is more stable? Well, in both cases, one of the groups must be axial. But in this case, the larger group is axial. Here, the larger group is equatorial. So this is going to be more stable because ethyl is larger than methyl. And in this particular ring flip, this chair conformation of this trans compound, my ethyl can be equatorial. Remember, both of them has one group equatorial, one group axial. I want the larger group to be equatorial. That's the more stable conformation. So you need to be able to analyze this. This is cis 1,4 di-substituted. Cis means I have up, up. This is 1, 2, 3, 4. So I have an equatorial methyl and an axial methyl, or I have an axial methyl and an equatorial methyl. Remember, this comes down, that goes up. This carbon is now this carbon. I still have equatorial up, and I have axial up. Which one is more stable? Well, here, they're equivalent. These are equivalent in stability because both have equatorial methyl and an axial methyl. If one of these groups were larger, the larger group would want to be equatorial. So you would have to decide which one you would prefer if they were not the same. Here I have an example of that, where one of the group is larger. Here I have cis 1-tert-butyl 4-methyl. So this is going to be 1, 2, 3, 4. It's cis. This is equatorial up. This is axial up. So that's up, up, which is cis. When I ring flip, this comes up, that goes down. My equatorial tert-butyl now becomes axial, and my axial methyl becomes equatorial. So now I have this huge group up here, and these diaxial interactions are huge. So this is less stable because the larger group is axial. This is much more stable because the large group is equatorial. So you're going to have to do this analysis on quizzes and tests in order to draw the appropriate chair ring conformations, including the ring flip, and then to assess stability based on the positioning of the substituents. Here's an example of a trans 1-3. Here I have 1, 2, 3. Trans means they're on opposite sides. So here I have equatorial up, axial down. I do the ring flip. This equatorial becomes axial up. This axial becomes equatorial down. Both of these have one axial methyl and one equatorial methyl, so they're equivalent in terms of stability. But again, what if I substitute the methyl on carbon 1 with a tert-butyl? I'm still trans. I have equatorial up, axial down. This equatorial becomes axial in the ring flip, right? This carbon goes up, this carbon goes down. You gotta play with this. You have to be able to draw these. You have to be able to draw the ring flip. So I have axial up, I have equatorial up. This is gonna be much less stable because the large group is axial. This is gonna be much more stable because that tert-butyl group is going to be in the equatorial position. Another example, this is cis 1-3. So I have 1, 2, 3. I can go 1, 2, 3 the other direction. It doesn't matter. I have both equatorial, right? This is down, this is down. That means it's cis. And then if I ring flip, I have down axial, down axial. Both of these are axial, right? So that's less stable. Both substituents are axial. Here, both substituents are equatorial. So this is much more stable than this guy here. In my trans 1-2 disubstituted, this is trans. I have equatorial down, equatorial up. I ring flip, I get axial up, axial down. Diaxial substituents, much less stable. Di-equatorial substituents, much more stable. You have to be able to withdraw all these two ring flips, assess their stability, and explain why one is more stable than the other using the correct terminology, including di-equatorial. This has 1,3 diaxial interactions. Use the word steric strain, torsional strain. You want to use the nomenclature that we've talked about in this class in order to explain what your answers will be. Here's another example of a 1,2 disubstituted, but this one cis. I have axial up, equatorial up. Ring flip goes to axial up, equatorial up. These are going to be equal energy and they're equally populated because in both of these conformations, one of the substituents is axial and one of the substituents is equatorial. So equal in energy because there's no difference between the stability of these two different ring flips of this molecule. Now, when I name a disubstituted cyclohexane, I need to use the prefix cis when there are two groups on the same side of the ring, and I have to use the prefix trans when I have two substituents on opposite sides of the ring. For example, both of these can be called 1,2 dimethyl cyclohexane. Both of those would fit the name 1,2 dimethyl cyclohexane. The cis says those two methyl groups are on the same side of the ring. The trans says those two methyl groups are on opposite sides of the rings. So these two compounds are not the same compound. I can't call both of them 1,2 dimethyl cyclohexane because the relationship in space is different. Same side, opposite sides. So what I have to do is use this cis or trans prefixes in order to designate between the two isomers. These are called stereoisomers, and because they're six-membered rings, they're best represented as chairs. You need to be able to name cyclohexanes where you have this difference, whether the substituents are on the same side or opposite sides. You need to use these prefixes, cis and trans, in your nomenclature when you're naming things that have obviously been specified as to which the substituents are on the same side or opposite rings. Now, anytime I have these two different isomers, the cis and the trans, each of those compounds is going to exist as two equilibrating chairs. That conformation that's most prevalent is going to correspond to the one that is the more stable chair conformation. So here I have axial equatorial, I have axial equatorial. These are going to be equivalent, right? One is always axial, one is always equatorial. Here, this is axial, this is axial, this is equatorial, this is equatorial. This is going to be the lowest energy isomer conformation for the trans isomer. All right. So draw the most stable conformation of the following molecule. If I want to do that, what I'm going to do is notice the relative stereochemistry here. So let's call this 1, 2, 3, 4, 5. And this is bold up. This is hashed down. This is bold up. This is hashed down. So what I'm going to do is I'm just going to arbitrarily draw one of my chairs. I'm going to put in all the axial and equatorial bonds in the appropriate way, no fishtails. And then I'm just going to arbitrarily say, all right, well, maybe this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And I'm going to put this axial up. On my second carbon, I have the methyl groups are on opposite sides, so this methyl group is down. On my third carbon, this is going to be up, so this is going to be the CH3, and this is going to be hydrogen. So I have up, up, up. Fourth carbon just has hydrogens on it. And then the fifth carbon, I have a hash down. So that's going to be my equatorial down has the methyl. My axial up has the hydrogen. So the ring structure that I get when I'm going to draw the other is going to look like this. And then this carbon and this carbon is the same. So this is going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So that axial is going to come up. This axial is going to come down. On carbon 3, which is here, that axial is going to become equatorial. Carbon 4 has just the hydrogens. And then this methyl group is going to be down axial, and that hydrogen is going to be equatorial up. Now, which one is more stable? I have an axial methyl, an axial methyl, an axial methyl, and equatorial methyl. Or I have an equatorial methyl, an equatorial methyl, an equatorial methyl, and then an axial methyl. This one has got more of the substituents that are larger than hydrogen in the same, or in the equatorial positions. So this is going to be more stable. This minimizes diaxial interactions and also minimizes steric strain. So this is going to be the more stable conformation. So you have to be able to do this. You should practice, and then you can check on this. Here's a few more questions that you should try at home. The last part of this lecture is just going to be talking about physical properties. Alkanes are non-polar compounds, right? I only have carbon-carbon bonds, and I have carbon-hydrogen bonds. Those are all non-polar bonds. So they have very weak interactions. These are only have London dispersion forces, right? I have very weak dispersion forces. These are those weak intermolecular forces of attraction from interaction of my temporary induced dipoles. So my boiling point is going to be relatively low. In fact, if I only have 1 to 4 carbons, these are going to be gases at room temperature because their boiling point is so low. So this would be methane, propane, and butane. If I have 5 to 7 carbons, they're probably liquids at room temperature. So it's a little bit higher molecular weight. So hexanes, decanes, gasolines, kerosene. And if I have 18 or more carbons, they're going to be white, waxy semi-solids or solids. Think about like paraffin wax. So again, think about why, if I only had 1 to 4 carbons, my low molecular weight alkanes would be such low boiling versus if I had 18 or more carbons. Remember, as I add surface area, I'm increasing the magnitude of the London dispersion forces. So there, it's going to take more energy to phase change from the liquid to the gaseous phase. So that's going to raise that boiling point. Density, they're less dense than water, which is about, water is 1 gram per mil. The density of alkanes is about 0.7. So liquid and solid alkanes are going to float on water. Constitutional isomers are different compounds and have different physical properties. Notice, these guys all have the same number of carbons. They have different branching. This is a great chart to know and to figure out why hexane has got the highest boiling point of them all. Remember, the greater the surface area, the greater the magnitude of those dispersion forces, and that results in a higher boiling point. So hexane is this long and skinny molecule, a lot of surface area. 2,2-dimethylbutane, which has the lowest boiling point, is more like a ball, right? I have less surface area in this situation, so my London dispersion forces is much lower. And then notice, as my branching changes, draw these out, make a model, and convince yourself that this is the appropriate order. I might give you something like this on a test and say, rank order these in order from lowest to highest boiling point and explain why you picked that order. So you'd have to draw the structures and sort of look at the surface area, and you'd have to figure out the branching, and you'd have to indicate that the compound that has the greater surface area would have an increase in those dispersion forces and a higher boiling point. And to explain all that, you not only have to draw everything, but you have to use the terminology. Now, reactions of alkanes, we're not really gonna focus on these. Alkanes are generally unreactive, except for a couple cases. Alkanes will combust. So oxidation is the basis of how we use alkanes, because we use them as energy sources for heat and power. So I can combust them and actually measure a heat of combustion, which is the heat that is released when 1 mole of a substance is oxidized to carbon dioxide. Look at the propane gas that we use in our grills on our decks. I have a lot of energy that is released when that combusts. Notice methane has a significant amount of energy. I get a lot of energy from the combustion of these molecules. These are negative numbers, which means the heat is released, that is exothermic. When you want to balance these, remember I always balance carbon, then hydrogen, then oxygen. That's a trick that you should have learned in Gen Chem, your prerequisite course. If the equation is still not balanced, usually I have some fraction, something over 2 oxygens. So to make that a whole number, all I have to do is double all the coefficients. Alkanes, these are sources of alkanes. In terms of natural gas, that's going to be 90 to 95% methane and 5 to 10% ethane. Petroleum, a lot of these will be gases that have a boiling point below 20 degrees. I can have these compounds called naphthas, which include gasoline, which are liquids. I have kerosene, which is another like lamp oil. I have fuel oil, lubricating oils, asphalt, which is the residue after distilling. Notice each one of these fractions that we're describing has a larger cut in terms of boiling point. And then I have coal. I can actually distill petroleum, and this fractional distillation means that I have this vapor, my crude oil gets heated and vaporized, and then just like we talked about in our separation of using distillation, this was gonna separate based on boiling point. So the stuff that'll come off first is gonna be my gases, which are in really low boiling points. And then notice that I'm gonna take cuts of the petroleum that have multiple boiling substances. So all of these are not pure substances, they're gonna be mixtures of different carbon content, different carbon numbers, but they all have their different uses. So I can actually cut them according to their boiling point, and they have uses based on that. And then the residue, the stuff that's left over, is going to be asphalt. So again, you want to make sure you know how to do these cyclohexane problems. So try these problems. This one in the slide deck, and then draw these guys and figure out which one is more stable. You want to practice this. You want to draw the chairs. You want to analyze them, and you want to figure out which of these conformations is more stable. If you have any trouble, make sure you reach out, because this is going to be a big part of our test. All right, thank you, and I will see you later. This is it for chapter 3. If you want more practice with those confirmations, you need to attend a Zoom hour, and we can go over them. And we can go over them in more detail. All right, good night.